in soil science, what we need to analyze is the content of nutrients in soils and plants. The contents of nutrients. So what are the nutrients that we are, or that are of interest to us? Those that are of interest to are NPK, calcium, magnesium, sulfur, zinc, iron, copper, manganese, boron, molybdenum, chlorine, and nickel. So there are 17 essential elements which are required for plant growth, and those we normally measure in our laboratories. But over and above these, there are heavy metals and certain elements which we also need to measure. So those new elements require sophisticated techniques for measurement, because not ordinary analysis won't cover them. So first of all, I will run through about what are the types of instrumental methods of analysis, and then we will straight away go to the emission methods. So what we try to do in a chemical analysis is we try to resolve the compound into its proximate or ultimate part. So either we analyze it completely, or we analyze it in such a way that we understand what is there in the sample. And there are two types, and these can be of two types. One is qualitative and one is quantitative. Qualitative means we just are interested in knowing what are the compounds present, and in quantity, how much of that compound is present. So these are the two basic types of analysis. And the things that we should take into consideration before going for any analysis is what is the information that is sought. So what is the sample size available? What is the proportion of constituents to be determined, and what is the purpose of this analysis? If I get a sample from Mars, and somebody gives you a sample from Mars, and you know that you cannot destroy that sample because that is a very, 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 very precious sample. So what you need to do, you have to try to find out methods of analysis which are non-destructive for those samples, because after you find out what are the nutrients present, somebody else will be using it, what are the microbes present. So the nature of the information sought, and the size of the sample available, and the purpose are all to be taken into account before we start any chemical analysis. So as I was telling you that it is proximate analysis, partial analysis, trace analysis, and complete analysis. In complete analysis, each of the elements present, A, B, C, D, suppose we have 4 constituents of in a compound A, B, C, D, then each compound A, B, C, D and their proportion, what percentage of A is in compound A, B, C, D, what percentage of B is in compound A, B, C, D. So each of it will have to find out to get that complete analysis. Whereas in proximate analysis, we do the analysis without having any concern of what is the quantity of that element A or B or C or D is present. Now, all instrumental methods are dependent on measurement of certain electrical property, or measurement of the extent of absorption, or measurement of the intensity of the emitted radiation. So these are the things that we usually measure using instruments. So these are the properties that we measure. And their advantage is that they are fast. We can analyze small concentrations, and we can automate them. That means you set it up at night and in the morning you get the results. However, their disadvantages is very expensive. It may run into crores. Calibration with appropriate standards are required, because it is an instrument analysis. Whatever you feed as a standard into that instrument, you will get your values accordingly. So if you have feeding a wrong standard, you get a wrong result. These are not suitable for analysis of small number of samples. For example, I want to do an NMR of one sample. So probably that lab, if I submit it into the lab, you will have to wait for a much long time, because to start an NMR, you have to feed argon gas and stabilize that instrument by working it for say 5 to 6 hours. So the instrument needs to stabilize. It takes say 5 to 6 hours, and then if you run a sample which will take say 5 minutes, and then you shut down that instrument, it is a wastage of money. So if you have large number of samples, that is suitable. Hence, normally in our laboratories, we combine both these methods, classical and instrumental methods. So because they supplement each other, we don't require instrument methods always, and we cannot do everything using classical methods, and hence a mix and match of instrumental and classical methods is preferred. Common techniques that are there, they are divided into 4 types. One is quantitative, then appropriate electrical measurements, measurements of some optical properties, and optical as well as electrical methods. So a combination of optical and electrical methods. So these are the 4 methods of analysis. In quantitative analysis, performance of a suitable chemical reaction, either measuring the amount of reagent needed to complete the reaction or ascertain the amount of reaction products obtained, that is measured. In appropriate electrical measurements, we measure either the current passing through or the voltage. Measure in the optical properties, we measure the what is the intensity of radiation passing through. So these are some of the things that we measure. In the first one, that is the quantitative, this one, the first one, A, the quantitative performance of suitable chemical reactions. What we do over here, this is actually traditional or classical chemical analysis. And here, suitable reactions are, we add certain chemicals to get suitable reactions so that the reaction gets completed. And then we find out what is the amount of the products that are formed, or how much chemicals that we have added results in the formation of that product. So that is how quantitative chemical analysis performs. They are of normally 3 types: gravimetry, tachymetry, and voltammetry. Gravimetry is nowadays no more used. It is, what is the main principle of gravimetry? The substance that we want to analyze, we first make a precipitate of it. We wash that precipitate of impurities, we dry that precipitate, and we weigh that precipitate. For example, potassium, before invention of say flame photometer and all, traditionally it would be done using gravimetry by combining potassium with silver cobalti nitrate, where potassium cobalti nitrate is formed, which is an insoluble precipitate. And this insoluble precipitate that is formed is washed and then dried and then weighed. So from the weight of the potassium cobalti nitrate, we can find out how much amount of potassium is there. Similarly, for sulfur also we can do the same thing. You know that sulfur precipitates as calcium sulfate. So you can precipitate calcium sulfate, dry that precipitate, weigh it, and find out how much amount of sulfur is present. And a special case of electrogravimetry, and special case of gravimetry is electrogravimetry, where the material is deposited at the electrode. You take up this electrode, you have an electrode, you weigh this electrode previously, and then allow the electrolysis to take place. And when electrolysis takes place, there is something which is deposited on this electrode. Suppose say copper metal is deposited at this electrode. So you know how much amount of copper metal. You take out this electrode, wash it, dry it, and then weigh it again. So the difference in weight of the electrode will give you the amount of copper that is there. Then you have titration and volumetric analysis. Here, the substance to be determined is allowed to react with an appropriate reagent added as a standard solution, and volume of the solution needed for complete reaction is determined. And the common types of reactions are neutralization reaction, complex forming reactions, precipitation reaction, and oxidation reduction reactions. The most common ones, the neutralization reaction, that is acid-base reaction, in which HCl and KOH react to form KCl and water. So this is a very simple acid-base reaction. This is we in our BSc AG classes we normally do this type of titration, titration of a strong acid and a strong base. So these are neutralization reactions. Then there are complex chromatic formation titrations for where we do calcium or calcium plus magnesium using EDTA. That is a complex formation takes place, so it's a complex chromatic reaction titration. Then there are precipitation titration where we do test for silver. Silver reacts with chloride to form silver chloride, and we add potassium chromate that gives you that brick red color. So that tests for chloride. The precipitates the indicator will color that precipitate, and you know that there is a precipitation, and you know that it is testing for chloride. Then there is oxidation reduction reaction, and even for organic carbon analysis, we do oxidation redox reaction. And potassium permanganate plus oxalic acid and oxalic acid, these reactions are all oxidation reduction type of reactions. So titrimetry is synonymous to volumetry. Volumetry is any method of analysis, quantitative chemical analysis, in which the amount of a substance is determined by measuring the volume that it occupies. So we measure the volume of the liquid, or we measure the volume of the gas. So that is by measuring the volume. Then there are electrical methods, which could be voltmetry, colorimetry, potentiometry, or conductimetry. Here we measure the current, voltage, or resistance. So in the first one, in voltmetry, we measure the current at a microelectrode at a specified voltage, whereas in colorimetry, we measure the current and time. And in potentiometry, we measure potential of an electrode. And in conductimetry, we measure the electrical conductance of the solution. So we normally, I do not know whether you have any idea of potentiometric titration or conductimetric titration. Instead of using an indicator, we can do the titration using potentiometry or conductimetry. That means we can do volumetric titration using potentiometry and conductimetry. So instead of indicators, we measure the potential, change in potential, we measure the change in electrical conductance. Then there are optical methods. These are dependent upon measurement of absorbed radiation, or there is emission of radiation. So it measures either the radiation that is absorbed or measures the radiation that is emitted. Now, absorption methods are classified into visible spectrometry, where if the wavelength of measurements are in the range of 400 to 760 nanometers. UV methods are if it is below 400, and IR methods are if it is more than 760 nanometers. So infrared spectrometry is used in organic matter, studies on organic matter and functional groups. UV methods are used in certain, night determination, if colorimetric determination of, say, nitrate or phenol. So you can do determination of various things using UV spectrometry. And normally we do all our phosphorus, sulfur analysis in the visible range. So atomic absorption spectroscopy involves atomizing the specimen in a flame and studying the absorption of radiation from an electrical lamp producing spectrum of that element to be determined. We'll come to atomic absorption spectrometry later on. Then there are turbidimetric and nephelometric methods that involves measurement of the amount of light stopped or scattered by a suspension. They are not strictly absorption methods, but you see there must be a difference made between turbidimetry and absorption methods. In absorption methods, it absorbs the wavelength, but in turbidimetric methods, it stops the wavelength. So determination of sulfur is turbidimetry, wherein you add, say, barium chloride to an element containing sulfur. So a solution containing sulfur, it forms barium sulfate. So these are small particles. These small particles do not absorb light, but they scatter the light and it stops the light. So if you do not do anything, these particles, this barium sulfate will settle down to the bottom as precipitate. But to keep it into solution, you add gum acacia so that it remains in solution, and then you can do this turbidimetric analysis. So it is because it develops turbidity We call it turbidimetric analysis. Then there are emission methods. Emission methods are based on the excitation techniques. We will come to flame photometry. There is emission spectroscopy. In emission spectroscopy, the sample is subjected to an electric arc or spark plasma. We will come to this one later on. And we have a fluidometry also, where there is the material that you are adding is fluorescent. So if you put visible or say UV light, it will glow. So examples are fluorescein and eosine. These are all fluorescent materials. So you can analyze various things using these. For example, the activity of microbes in solution can be done in this way. Umbelliferon is a pigment found in the wings of butterflies. So this is also a fluorescent material. Then there are various other methods such as chromatography, X-ray methods, X-ray diffraction spectroscopy, then radioactivity, mass spectrometry, and thermal methods like TG, DTA, and DSC. So there are so many methods, and the analytical methods are adding up every day. So each day you get a new method of analysis. So the field of instrumental analysis in soil science is expanding at a very rapid pace. So it is difficult to keep pace along with this. For example, I will tell you that a spectroradiometer is a new device that is being used in soil science and plant research. It measures the reflected radiation, and using that you can calibrate your instrument to be able to predict various nutrient contents in the soil, as well as say chlorophyll content in the plant, or you can forecast yield. So we have done modeling of say nitrogen, phosphorus, potassium, sand, silt, clay using spectroradiometer. It's a very useful device. Then there is X-ray fluorescence method. That is another method which is coming up. So there are n number of methods that is coming up in the field of soil science now. Now, what would be the factors that affect the choice of analysis? The type of analysis required, the problem arising from the nature of the material to be investigated, if there is any interference, concentration range to be investigated. What would be the range of concentration? What is the accuracy required? What are the facilities available with you? And what is the time needed to complete that analysis? A number of samples of similar type that have to be performed, and non-destructive or destructive methods to be used. So these are some of the things that you should keep in mind. And on this will make the factors affecting the choice of analysis. And finally, whatever results you get, you have to be very accurate and precise both. Accuracy is correctness of measurement, and precision is reproducibility of measurement. For example, if the correct value of any analysis is say 10, I'm leaving out the unit, and an analyst A measures it 4 times, and each time he gets a value of 12. So he has measured precisely. That means each time he has measured, his results are reproducible. It is the results are away from the actual results. The actual result is 10 and his result is 12. It is away from the actual result. It is not accurate, but it is precise. Another analyst does it 4 times. In one, he analyzes 6, 8, 12, and 14. So he gets 4 values, 6, 8, 12, and 14. And you take an average, it will give an average of 10. So that means this analyst B, he measures 4 times, and each time his analysis is different. So that means he's not precise, but the average of his values are exactly same as what the actual value is. So he's accurate. Now, what do you want in your analysis? Do you want accuracy? Do you want precision? We actually want accuracy as well as precision. But for certain analysis, it would be good to have reasonable amount of accuracy and a reasonable amount of precision. It's good to have 100% accuracy and 100% precision, but that is a hypothetical situation. If you want to have a good amount of accuracy and good amount of precision, you have to compromise on both accuracy as well as precision. Otherwise, your cost of analysis becomes very high. Okay. With that, now I was telling you of the emission methods. The first emission method, the simplest one, is the use of flame photometer. Is the use of flame photometer. Okay. Just give me 2 minutes. Okay, sir. Okay, sir. I have a call to attend. Okay. Okay. Then we have 3 commonly used emission methods. One is flame photometry, second is atomic absorption spectrophotometry, and third is the inductively coupled emission spectroscopy. So these are the three commonly used emission methods. And first I will run through 1, 2, and 3, that is flame photometer, atomic absorption spectrophotometer, and ICP, and then I will compare what are the things that are common in them and what are the things which are not common in them. As the name indicates, it's an emission method, and it can easily determine elements. Now, which elements? Those elements which can easily be excited. And what are those elements which can easily be excited? Elements which have only 1 or 2 electrons in its outermost shell. What are those elements? Those elements, those that reside in group 1 and group 2, group 1A and group 2A of the periodic table. And what are those elements? These elements are lithium, sodium, potassium in the group 1, and calcium, magnesium, strontium, and barium in group 2. So they have 2 electrons in this outermost shell, and energy provided by the flame is good enough to send these 2 electrons or 1 electron of these elements to an excited state. So that forms the basis of flame photometry. Now you must remember the flame test. In your 10+2 classes, we have done the flame test where we introduced, where we can introduce some chemical into the flame and it gives us the color. And from the color, we can find out what is the element, what could be probably the element. That means flame tests helps us identify unknown compound metal in the compound. So whenever you introduce that unknown compound into the flame, the metal will glow with a characteristic color. And that is why in fireworks, we use different types of metal chips so that we get different types of colors. Now you can see burning elements would produce different colors of the flame, and they correspond to different elements. So if you knew what color of the flame it is, what is the color of the flame, you can probably find out what is that element that is associated with the compound that you are introducing into the flame. Now some basic theory. What is spectroscopy? It is the use of absorption, emission, or scattering of electromagnetic radiation by atoms or molecules to qualitatively or quantitatively study the atoms or molecules, or to study the physical process. Now, what we are interested in, qualitatively means we can, the flame test. You just insert it to the flame, we can know, okay, this could be the metal present. Quantitatively means we want to know how much amount of it is there. Okay, come to flame photometry. Now, when matter interacts with radiation, when radiation interacts with matter, many things could happen. It could cause redirection of the radiation. It coming here, it goes this way. Or it could cause a transition between the energy levels of atoms and molecules. It's at a given energy level, takes up energy, goes to a higher energy level. So these are a transition from lower to higher level with transfer of energy from radiation field to the atom or molecules is called absorption. And the opposite, that is from higher level to lower level, is called emission. If the transfer of energy, if the energy is transferred into the radioactive in the radiation field, if you can feel that radiation, or it is a non-radioactive decay if no radiation is emitted. So once there is an atom it absorbs energy, goes to a higher state. So at the higher state, it is called the excited state. So this is absorption of energy. So when it comes back to the ground state, it emits radiation. If it emits radiation, it is radiation. If it doesn't emit any radiation, and if you don't see that radiation coming out, it will be called as non-radioactive decay. There could be redirection also. Redirection of light due to its interaction with matter is called scattering. It hits this place and goes this way. So it's scattering. And this may or may not occur with transfer of energy. That is, scattered radiation has a slightly different or the same wavelength. So there is no change in wavelength in scattering. This is picturically shown over here. This atom has only one electron, which is yellow in color, and this is its ground state where it revolves in over here. Now, as and when you add some photon, you hit some photon, that means some energy is given to this electron gets excited and goes to a higher energy level. So this is a lower energy level, this is higher energy level. So if it is E1 and if this is E2, then from E1 it goes to E2. So it goes to E2, but it is a very transitory state. It cannot infinitely keep on moving in E2. It will have to come back to its ground state. So as and when it comes back to the ground state, it gives out radiation again. It gives out radiation again. This radiation and this radiation is not of the same wavelength. The wavelength that is given out by this atom is characteristic of this atom, because it is characteristic of this and this. That means E1 and E2. And each element has its different energy levels. This is what is shown over here. If you have an atom in the ground state, and when radiation comes over here and hits this atom, it absorbs the radiation, goes to an higher energy state. This part is called absorption. But this is a transitory state, and the difference in energy between these two states is delta E, E1 and E2. So difference in these two states is delta E. But this is a transitory state, and it comes back to the ground state after some time, and it's denoted by H nu. Okay, so this is emission. So this part is absorption, this is emission. Now we can simply mathematically we can say that the difference in the energy state of ground and excited state, that is delta E, which is equivalent to ground state minus excited state, is equal to H nu, where H is the Planck's constant and nu is the frequency. Now H is a constant, and hence delta is directly proportional to the frequency of the emitted radiation. Now we can change this frequency because velocity of light c is equal to h into nu. C is equal to nu into lambda. So we can have nu is equal to c by lambda. So we can, instead of nu, that is frequency, we can write wave c by lambda. C is the velocity of light and lambda is the wavelength of that radiation. So h and c is again Planck's constant, and velocity of light both are constant. So you have delta E is a function of the wavelength of emitted radiation, because wavelength is what which can perceive. Or rearranging this one, wavelength of that emitted radiation is equal to a constant by delta E. That means it is characteristic of the change in state or difference in state of the two ground and excited states. So each element will have different ground state energy level and different excited state energy level. So delta E for each element will vary, and hence wavelength for each element will vary. And that is why you can see yellow colored radiation, yellow colored radiant energy of sodium when you introduce sodium into the flame. That is because the color that is that the wavelength of light that is emitted by sodium when it comes down from the excited state to the ground state is in the region where it gives yellow color. So that is the importance of your this equation. Wavelength of emitted radiation is inversely proportional to the change in energy of the ground and excited state. Having said this, when atoms or molecules absorb light, the incoming energy excites them to a higher energy level that we have already studied. And the type of excitation depends on the wavelength. What type of light is coming and hitting that electrons? If it is, say, visible light or ultraviolet light, those electrons will move to higher orbitals that we have just now discussed. But if instead of visible or ultraviolet light, if you apply infrared light, then instead of going to higher energy levels, it will start vibrating. It will start vibrating at its own place. Whereas if you apply microwaves, then it will start rotating. So there are three types of phenomenon that could be done. Suppose if you use UV or visual light, then we can do what is being done over here. If you use infrared light, then there will be vibrations, and with these vibrations, normally we use these vibrations for some other purpose, to find out some, say, functional groups and all. So these are the three types of things that can be done, that can happen. Now, then what is the principle on which a flame photometer works? So we have the solution of that element which we want to measure, and we spray a solution of fine particles in, say, gaseous form state, and we nebulized it just like spraying perfume. So you have small droplets. Now these droplets are introduced into the flame. Flame is hot, so this what will happen? This water evaporates. So it will get desolvated, and here you will have the solid chemical or aerosol of the chemical that you have put in the solution over here. So from here it will form molecules, and from molecules it will form atoms. So molecules also can be excited. It will give you molecular excitation. Atoms can be excited and it will give you atomic excitation. We are interested particularly now in this one, atomic excitation. There could be ions also at even higher temperature. It could form ions, and when it forms ions, there could be ionic excitation. So you see, depending upon lower temperature, molecular excitation, even higher temperature, atomic excitation, and at more higher temperature, ionic excitation. So this is where the ICP works, and this is where the flame photometer and the atomic absorption spectrophotometer works. So this range. Giving the example of calcium, you will find that when it is that each of these have different wavelengths. So say if it is a calcium ion, the wavelength will be different. If it is a calcium atom, the wavelength will be different. If it is a calcium oxide molecule, the wavelength will be different. So molecular, atomic, and ionic absorption are all different. Okay. This is I think I have already told you how it is done. The first step is the solvent is vaporized, leaving the solid salts. Then it is converted into the gaseous state. It forms molecules. Molecules forms atoms. And these neutral atoms are excited by the thermal energy of the flame, and the excited atoms which are unstable. Now, here is what we are interested in. These unstable excited atoms will quickly come back to its ground state. And when it comes back to its ground state, it will give out photons. And these photons that are given out are emitted, are measured. This is what we measured in flame photometry. What are the components? Components are pressure regulator and flow meter, atomizer, burner, optical system, photosensitive detector, amplifier, and readout device. These are some of the components. This is a simplified diagram. Here you have the flame. You insert a solution of the element that you want to measure into that flame. Here it is excited. The atom is excited, comes back to the ground state, and emits radiation. This emitted radiation is collected in a detector, collected through a detector, and we measure the amount of radiation that is given out. Now, first thing that you have is the pressure regulator and flow meter. Among the components, you find the pressure regulator and the flow meter. Then the atomizer. The most important part is the atomizer, as I will tell you. First is the pressure regulator and flow meter. You will find normally this one outside the instrument or at the back part of the instrument. So you have suitable gauges and inserted into that instrument so that you can see the meter is over here. So these things, what we will do, it will send the air and the gas at a constant pressure each time you set that or make that operation. That means you can set it at say 0.4 or 0.5. So depending on that, the gas flow and the air flow will change. So you can change the sensitivity of the instrument also to some extent using this one. So that between measurements, there is not much variation. We generally try to keep it at a fixed level. We try to keep the pressure regulator and the flow meter at a fixed level so that each time we start the analysis, you put up the instrument, start that instrument, each time you do that analysis, the flow rate remains same. Now, this is the heart of that instrument, the atomizer and the burner. Atomizer introduces the liquid sample into the flame at a stable and reproducible rate. And there are two types of atomizer. One that introduces the spray directly into the flame. One, it mixes the spray in some place and removes big droplets and allows only the very fine droplets to reach the flame. So these are two types. The first one, which is the second one, which is the total combustion burner, allows all components to be mixed and introduced into the flame at the same time. What it does, you have concentric rings, first outer ring, inner ring, and very fine inner ring. So there are three things like that. For example, if you have a pen and say, so if you have a pen, something like this, you can have say one outer tube, one inner tube. So you can have one more tube through this. So there could be three concentric tubes. This is what is depicted in this picture. You have three concentric tubes. One is the very inner tube through which the sample solution comes. There is the fuel and the oxidant. Oxidant is air in this case. We pump in air. So as you pump in air, and since it is constricted, there will be low pressure formation because of Bernoulli's theorem. The gas flow will be something like this. So air pressure converges and maximum air pressure, and as it leaves the nozzle, air pressure goes down. So here there will be a vacuum sort of thing created over here at the mouth. So because of this, liquid from the sample chamber will be sucked in through the capillary, and over here, as it is forced through this place, it breaks up into small droplets. And the gas and the oxidant all mixed with this sample burns in the flame. Now, this drawing up of the sample and breaking up of the sample, introducing these droplets into the flame is not uniform. And that is why you will find that the flame is not very stable. It will be going up, down, up, down. So it will be a bumpy flame. A bumpy flame doesn't give good analysis results because that is detected by the detector and there are variations in your reading. Here, all the samples will be carried to the burner. The advantage, what is the advantage? Disadvantage, I've told you that gives bumpy flame, gives extra turbulence, and there is no uniformity of the drop size of the sample. This is the disadvantage. Advantage, it is very cheap and all the samples will be carried out. So little amount of sample also that you are applying will be reaching the flame. There is no wastage of sample. Then you have the second type or P-mix burner. This is a system where there is a chamber, where there is a mixing chamber. So here the sample, fuel and the oxidant, they are all mixed in this region. And these are baffles, and this mist can travel through this place here. Okay, so the bigger droplets will go through down the drain, and the very fine droplets will move through the baffles and reach the flame. So this is how this works. The sample fuel and oxidant are mixed prior to the entering the flame, and the turbulence drastically reduces because large droplets are removed through the drain. So what you will find over here, very mist type of particles that will be reaching the flame. So here the efficiency is low because you are losing much of your samples. Your samples are introduced, it will go through the drain. Much of it will go through the drain. Only a few, small part of the samples will reach the flame. But it gives a steady reading because the flame doesn't bump. So that is the heart of the instrument, which produces the small droplets, and it also helps in burning. So here is where the radiation, that is emission of radiation, takes place. So in the flame, it is oxidized, it goes to higher energy state, comes back to the ground state, emits radiation. And this radiation, emitted radiation, has to be read or detected somewhere. Where it is done by the, it passes through the optical system. And the work of the optical system is to collect the light radiation from the steadiest part of the flame and focus it onto the detector. So it does, its function is to collect the light from the steadiest part of the flame, render it monochromatic, and then focus it on the surface of the monochromatic detector. Now, monochromatic means mono means one, chroma means light. So light of a particular wavelength. So potassium has a different wavelength at which it is measured. Sodium has a different wavelength at which it's measured. Each element has a different wavelength at which it is measured. And hence, because the light wavelength lambda is inversely proportional to delta E, so I told you that each element has a specific wavelength of light emitted. So if we want only that wavelength to be measured, then we put a filter in between the flame and the detector. So only radiation of potassium can pass through this filter. Filters are called monochromatics because they allow light of only particular wavelength to pass through. So that is why in a flame photometer, you might have noticed that there is a disc that is to be rotated before starting your analysis work. As you rotate this disc, in this disc you have different filters. You could have filters of potassium, sodium, lithium, calcium. So as you rotate this disc, colored glasses of different colors will come in between the flame and the detector. So what will this colored glass do? This colored glass will allow light of only particular wavelength to pass through it. Okay. So the function is to collect the light from the steadiest part of the flame, render it monochromatic, and then focus it on the surface of a monochromatic detector. And a concave mirror is often placed behind the flame here, with its center of curvature in the flame, so that it collects. So flame is over here and your concave mirror is over here. So flame is here, concave mirror is here. So light from the flame will hit this one and go straight. So that is what the concave mirror does. It will allow maximum amount of radiation collected from the mirror from the flame to go to the detector. Absorption or interference filters may be used to isolate radiation characteristics of a given element which has a simple spectrum. So say for example, potassium, you have a potassium filter. For sodium, you need a sodium filter. So these filters that gives monochromatic radiation, that allows you put white light, that means mixture of all the wavelengths, put a filter, white light of only a particular wavelength will pass through. So that is a work of a filter. So absorption filters could be of different types. Absorption filters absorbs other radiations and only allow radiation of a particular wavelength to pass through. Whereas interference filters works by the process of constructive and destructive interference. That means when light waves come and there is a small hole, it passes through that hole, and at the different edges there will be interference, and this interference could be constructive. If it is constructive, it will be enhanced. If it is destructive, the waves will be destroyed. So they have been used as monochromators also. So this is an example of optics. So here is the burning chamber. This is the flame. Here it burns, and from the light collected from the steadiest part of the flame is then moved on to the photomultiplier tubes, which are nothing but the detectors. Now the detectors could be a photomultiplier tube or a barrier layer cell. The barrier layer cell has different materials. Over here, when photons fall onto this material, it liberates electron. When photon falls onto this material, which is a semiconductor, it liberates electron, and this electron can be collected. If you connect it through a circuit, electrons will flow through this circuit. If you put a galvanometer in between, there will be deflection in the galvanometer. So as and when one photon passes and hits this place, one electron will move into the circuit. If two photons pass, two electrons will move. Three photons pass, three electrons will move. So the galvanometer will be deflected more and more. This is the basis of working of a barrier layer cell. Phototube, even a single electrode that is focused, say this is the single electron, single photon coming, it can be multiplied by a series of di-anodes. So each one multiplying it, doubling it. See, 1 will become 2, 2 will become 4, and ultimately here at the end, or the collecting end, we get a cascade. So we have a cascading effect. That means, yes, that means a single photon, even a weak signal, can be multiplied and we get a strong signal. These are the function of a detector. Now, what are the limitations? These are not suited to atoms that require large energy for excitation. For example, the transition metals, and this is limited to group 1 and group 2. Group This is only suited to group 1 and group 2, but if we put group 1 and group 2 in plasma, we actually, I showed you there, at a higher temperature, we ionize them. We do not get the atoms, we generate ions, and ionic spectra is different from atomic spectra. So if if some amount of ionization has taken place, there will be problems or interferences. Ionization causes complete change of energy level and therefore the entire emission spectrum with a reduction of intensity of the atomic spectra. So atomic spectra decreases, ionic spectra increases. So there the comes in the interference. Moreover, this tells us about, this method of analysis tells us about the total metal concentration of the sample, not the molecular form. You won't get the molecular form of that sample. So what was the original constituent, you cannot say. It will give you the total total metal concentration of the sample. Okay, so with this we finish flame photometer. Now this is a simple technique. The cost of a flame photometer is say around 40,000. So that means by using a flame photometer, it's a cheap instrument, you can measure the elements which are easily excited, which are group 1 and group 2, group 1A, group 2 of the periodic table. And this is based on emission. That means absorption of radiation from a ground state, getting excited to an excited state, coming back to its ground state, and giving out this energy. This energy that is given out is directly proportional to the amount of element present in the sample. So more the amount of elements present, more will be the emission, and hence you will get more reading. So that is how we analyze the samples. So this is the basis. Then slightly higher slightly more advanced instrumentation is the atomic absorption spectrophotometry or spectroscopy, whatever you call it. And what is atomic absorption spectrophotometry? It is spectroscopy. It's a quantitative method of analysis that is applicable to many metals and a few non-metals. So metals as well as non-metals can be analyzed using an atomic absorption spectrophotometer. In contrast to atomic emission spectroscopy such as the flame photometry, atomic absorption spectroscopy in terms of analytical method is a recent technique. It was only in 1955 that Walsh from Australia, he gave this technique. So you see, it's a comparatively newer technique. So Alan Walsh actually published a paper, application of atomic spectra to chemical analysis in the year 1955. And he further went to make an instrument in his laboratory, which was made by Alan Walsh. You can see this is so crudely made. And this is the detector. These are the controls. And here you have the what you call nebulizer, which sends that element into the flame over here. And here you have the flame. Here you have the hollow cathode lamp. I will come to that hollow cathode lamp. And here you have what you call is that flame. This is the first commercial prototype that was sent to the market for analysis. So this is the first commercial prototype. That means this is going to the market for selling. And this is an example of the new instrument that is there in our lab now. It is a modern instrument of Varian. Now this is the most powerful technique for determination of say 60 to 70 elements in trace and macro quantities in liquid samples. So this is to be kept in mind. So we use only liquid samples over here, but later on you will see that there has been modifications where solid samples as well as slurries can be introduced into the for determination. Then there is direct application to limited to metals. The direct application is limited to only two metals, but certain non-metals can be converted into their hydrides and they can be analyzed. So this determines the metal content of a sample, which is independent of the molecular form of the metal in the liquid. So again here, the molecular form of the metal is not taken into consideration. It determines the total concentration. For example, if I want to find out how much of ferrous iron is there in the sample or how much of ferric iron is there in the sample, you won't be able to say how much of ferrous or ferric iron is there. You will say that only the total amount of iron present in the sample is so much. There is very little interference and little sample preparation is required. So that is a very big advantage. And hence, this has been put to a lot of use. So what is the principle? When a solution containing metallic species is introduced into the flame, vapors of that metallic species is formed, similar to that of flame photometer. Some metals may be excited, but here you see, there we depended upon excitation. But here, only some metals may be excited, but most remain in the ground state. So 1 or 2% of the metals will become excited, but most of the around 99% of the metals will remain in the ground state. So flame photometry cannot utilize this technique, but there is a roundabout in this technique. The ground state atoms can receive light radiation of their own specific resonance wavelength. Now you must need to know what is own specific resonance wavelength. Remember lambda? Lambda is equal to a constant by delta E. That means that lambda is specific for a specific element. So that when excited, that element will give out that lambda. Conversely, that element can also absorb light of that specific wavelength, and that is called the resonance wavelength. You know resonance, that two wavelengths will of similar amplitude, when they are superimposed on one another, they will move, or they will add up, and the wavelength frequency will increase a lot. Similarly, here that analogy has been used over here, that the element which gives out a radiation of a wavelength lambda can also take in radiation of that same wavelength lambda. and that wavelength is called resonance, specific resonance wavelength. Now, the principle over here is, since 99% of the atoms remain in the ground state, we do not make any attempt to get it excited and bring it back to the ground state. No. Instead, what we do is we send in light of own specific resonance wavelength, and these atoms can absorb that light. So how much amount of light is absorbed? You just find out. That is as simple as that. Now, atoms in the flame absorb this light, and the absorption is proportional to the density of atoms in the flame. So if there is nothing in the flame, even if you put in any amount of own specific resonance wavelength, nothing will be absorbed. If there is one atom, say one atom will absorb, say, one photon. Two atoms will absorb 2 photons. Three atoms will absorb 3 photons. 30 atoms will absorb 30 photons. Now I am giving out 100 photons from my source, and I am collecting over here. So I'm giving out and collecting. Now in between, some goes missing because someone is absorbing it. So when there is nothing, I give out 100, I get 100. So no problem. When there is one atom, I give out 100, I get 99. When there are 30 atoms, I give out 100, I get 70. So that forms the basis of measurement. The atoms in the flame absorb this light, and the absorption is proportional to the density of atoms in the flame. Total amount of light absorbed at a given frequency depends on number of atoms present and their absorbing capacity. We don't want to go into much details. Same thing happens over here. The solution that you are putting in, it is first desolvated, then it becomes aerosol and solid particles, it becomes gaseous, it becomes atoms, and these atoms will be in the ground state. Atoms will take in radiation of its own specific resonance wavelength. Same slide. Now these are the components. Here, from here to here, everything is same. From here to here, everything is same. Only difference is that the light that we put in is from a different source, and we call it the hollow cathode lamp. So the radiation source is a hollow cathode lamp or an electrodeless discharge lamp. That is a newer version of the hollow cathode lamp. So a hollow cathode lamp, light from a hollow cathode lamp will pass through a lens and through the flame where the atoms in the ground state are. So depending upon the atoms present in the ground state, they will absorb light or a specific resonance wavelength of light that is passing through them. And the remainder of the light will reach the detector through the monochromator. Why the monochromator is required? Because each element has an own specific resonance wavelength. Suppose element X has a wavelength of 300. So I need a monochromator that allows, say, around 299 to 301 nanometers to pass through. So only 300 nanometers radiation will pass through and will be reaching the detector. Now detector doesn't have selectivity. Whatever will reach the detector, it will then reach. So in this light from the source is directed to the sample to a detector. The greater of the amount of sample present, the greater is the absorption produced by the sample. So this is the an old instrument. Here you will see that this is a light from where the light source comes. This is the sample compartment. This is the detector. This is the readout device. If you see that next, so here this is instrument is not working. Here the instrument is working. So you will see that light is coming through this one, and this is the flame. Here this is the flame. So here you have the sample introduced into the flame and the light passing through the flame. Now where does this light come from? The light comes from the hollow cathode lamp. Source of light is the hollow cathode lamp. Why is it called hollow cathode? Because the shape of it is like a hollow cathode. The cost of this instrument goes up because for each element we need a specific resonance wavelength, and hence we have to give a different light source. For example, if I want to measure iron, I have to use the hollow cathode lamp of iron. If I want to measure aluminum, I will have to use a hollow cathode lamp of aluminum. So you have to change the lamp before each analysis. So you see, these are the place where the lamps are housed. This is the housing of the lamp. This is like a turret of a machine gun. So it will move. It will move like a machine gun. So suppose I want zinc, and this is the zinc one. So it will move and come in position before the analysis has to start. So this is one type of instrument. In the other type of instrument, all the hollow cathode lamps are glowing at the same time. So here, this is a smaller instrument where 1, 2, 3, 4 lamps are there. This is a bigger instrument where we have many lamps placed. And what we do is we have a mirror over here. Suppose I want this light to go through the flame. So light from here, the mirror will be placed at such an angle that light reflected through the mirror and will go straight through the lamp. Here, while using this one, it will be moved. This mirror will be moved in such a way that it will be reflected and moved through the flame in this direction. So by the rotation of the mirror, the items in the radiation from the flame can be moved. Advantage of this instrument is that without changing the lamp, we can do the analysis of the number of elements that we have the lamp switched on over here. If we have 5 lamps switched on, we can measure 5 elements at one time. Whereas for this one, you will have to stop that instrument, change the electrode for each time you measure that element. So these are actually discharge lamps. Hollow cathode lamps are discharge lamps. They are made of an anode and a cathode. This cathode is hollow in shape. That gives the name of hollow cathode lamp. And you have a window and a glass envelope. Window means this is also made of a different type of glass, which allows radiation to pass through. That is why it is called a window. How does it function? You have a rear gas over here, a rear gas. That means argon, say. The electrical discharge ionizes the rear gas atom. So inside there is a rear gas atom at a low pressure. So when you make an electrical discharge over here, when you connect the anode and the cathode to the high voltage, it causes a discharge. So this discharge from the anode will first ionize the heavy metal, the inert gas, say argon, inside this chamber. When it becomes ionized, it will be attracted to the cathode, and while going to the cathode, it will hit other argon atoms and get them ionized also. The electrical discharge ionizes rear gas atoms, which are accelerated to the cathode and sputter metal atoms into the gas phase. So from here, first argon, which is inside here as a gas, it is first ionized. When it is ionized, it becomes charged and is attracted by the cathode. So it goes and hits the cathode. As it hits the cathode, it dislodges some metal ions from the cathode, of which it is made. So the solid metal of the cathode over here will be dislodged and it becomes gas. And this gaseous metal can then be excited by collision of high-speed argon atoms. And when this excited atom comes back to the ground state, it gives out radiation, and this radiation will pass through, because this radiation will pass through this window, will go straight, because from these regions, these are opaque regions from which radiations cannot move, which cannot travel. Only this part is where the radiation can move, and hence it is called a window. So you understand, this is the most important thing that happens inside the instrument of a hollow cathode lamp. It is a hollow cathode lamp is the main thing of that instrument because it produces the specific resonance wavelength. First thing is that there is an anode and a hollow cathode, and it is encased in a noble gas, say argon, under low pressure. Whenever you give a potential difference, then there will be electrons will move from the anode towards the cathode and first hit the argon. When it hits the argon at a very high speed, argon gets ionized. That means it becomes charged. As it becomes charged, it is attracted by the cathode. While going towards the cathode, it hits other argon also, and so these ionized argons will go and hit the cathode. As it hits the cathode, it dislodges some atoms of the cathode, and these dislodged atoms of the cathode will be hit by other electrons and other ions, say, of argon. So when they are hit, they become excited, it goes back to the ground state and gives out the radiation, which is the specific resonance wavelength of that metal M. So M will have a specific resonance wavelength. So M will have a Hc by lambda, that will wavelength specific to M. That is why for each element you need to change, because this value is different for different elements. That is why it's called specific resonance wavelength. Now, and advancement with better. The problem is that because these metal atoms are dislodged from the cathode, so after some few cycles of operation, the cathode becomes useless because it will be decaying. So you have your life of the instrument.
Sir.
Yes.
Sir, you are saying the emission released at HV is the no, sir?
Yeah.
That emitted radiation is the thing will hit the flame, sir?
Yes.
Okay, sir. That emitted radiation is the thing that hits the flame which we made with a sample, and it passes through the this.
If you see this photograph, this photograph, so there is liquid here. So this is sprayed into the flame. So what you have, in this flame is a fine spray of the element you want to measure. For example, I want to measure iron. I make a solution of iron over here, and this is sprayed into the flame. So you will have atoms of iron in the flame. You will have atoms of iron in this flame, and these atoms of iron are not excited. Mind it, only 1% of them are excited at this flame, because the flame temperature over here is very high, around 2000 degrees centigrade. But even at this temperature, say 2000 to 2700 degrees centigrade, but even at this temperature, atoms of iron are not excited. Only 1% are not excited. Only 1% of the atoms are excited. Rest 99% of the atoms are in the ground state.
Okay, sir.
Okay. Now, these atoms which are in the ground state, they can absorb light of their own specific resonance wavelength. You get my point?
Yes, sir.
So I now need to give specific resonance wavelength of iron through this flame. And this diagram shows us exactly this, because here is the lamp compartment, and this hollow cathode lamp will cause the discharge, and this discharge will pass through the flame. It passes through the flame, and while it passes through the flame, these unexcited atoms, that means atoms of iron which are in the ground state,
Ground state.
they will absorb radiation of specific resonance wavelength of iron. वेट करो थोड़ी देर पे और क्लास खत्म हो जाएगा थोड़ी देर में, वेट करो लैब में. Understood what I want to, what I'm trying to say?
Yes, sir.
You are not exciting the atoms over here. In flame photometer, we excite the atoms to a higher energy state. When they come back to the ground energy state, it gives out radiation, which is measured. Here we do not do that. Here, even with all our efforts, the atoms will be in their ground state. 99% of the atoms will be in the ground state. And these ground state atoms can absorb light of their own specific resonance wavelength. So we need to supply light of their own specific resonance wavelength through the flame, because the atoms are in the flame. So we need to pass that light through this flame, and we do that by using a hollow cathode lamp. And I just told you how a hollow cathode lamp functions. It has a cathode and an anode, and when I connect them to the electrical circuit, it gives out electrons. And since the atmosphere is argon, the argon is first ionized. This ionized argon molecule will hit the hollow cathode, and while it hits the hollow cathode, it dislodges the metal from that hollow cathode. That means if I want to analyze iron, I will have to have a hollow cathode lamp made of iron, because the hollow cathode lamp, iron of that hollow cathode lamp will be dislodged. This atom is dislodged, and this is again hit by ionized argon. So it gets energy, lot of energy. That is atomic collision, high energy. That makes iron excited. But anything which excites comes back to the ground state. When it comes back to the ground state, it gives out radiation. It gives out radiation characteristic of iron. And that is what you can see in this flame. So when it passes through the flame, the atom can absorb, atoms of iron in the ground state can absorb radiation of the specific resonance wavelength of iron. Do you get it?
Yes, sir.
Okay. But the problem is that since metals are dislodged each time you use the lamp, then this hollow cathode will slowly will be losing atoms from here, and hence it will be decaying. That means you cannot use the hollow cathode lamp for a very long period of time, because its efficiency decreases with dislodging of atoms from the cathode. Hence, you need to change the hollow cathode lamp at a definite interval of time. Okay. Now, to overcome this, there are new lamps in the market which are called electrodeless discharge lamps. And the radiant intensity of radiation used in these lamps are greater than that of hollow cathode lamps. So they have higher efficiency. Now, typical construction is you have a sealed quartz tube containing inert gas argon at low pressure and a small quantity of metal salt whose spectrum is of interest. For example, if I want to analyze iron, I have iron salt into a sealed quartz tube with argon in low pressure. Now, in the previous case, energy was provided by colliding ions of argon. Here, we use a radio frequency or a microwave radiation that is very intense, that energizes the argon, which goes and hits the iron, and then iron gets excited. So argon over here at this very high frequency becomes plasma, and it transfers that energy to iron, which can then become excited, and when it comes back to ground state, it gives out radiation which is specific to iron. Okay, so there is a difference over here between hollow cathode lamp and electrodeless discharge lamp. In the hollow cathode lamp, the energy involved is not so high. In electrodeless discharge lamp, you have a sealed quartz tube wherein you have argon and you have the metal salt of your interest. It is enclosed in this way. And then you apply radio frequency or microwave radiation wherein argon becomes heated to a very high temperature, it becomes plasma, and at that high temperature, your iron salt will also become excited. It gives out radiation, comes back to the ground state, and then gives out the radiation specific to iron. So these are the light sources. So this is the electrodeless discharge lamp. Here you have the sealed tube, wherein you put your argon and the salt of interest. And this is the radio frequency coil, this coil, which is surrounded. Now, we have emission coming from the flame. We need to remove the atomic. Now, why is it called atomic absorption? Because iron that we are trying to analyze is absorbing radiation of its own specific resonance wavelength from the electrodeless discharge lamp or the hollow cathode lamp. That is why it is called atomic absorption. It absorbs energy. It absorbs energy of its own specific resonance wavelength. That is why it is called absorption. But there is emission also taking place in the flame, and that emission also reaches the detector. We are not interested in that. So what we do, we put a chopper before the flame. Chopper is nothing but a fan blade. It chops the flame. Chopper is used to break the steady light from the lamp into a pulsating light. So if say light is coming here and I use a chopper like this, so sometimes light will not pass through, sometimes light will pass through. So the resulting thing that you get is sometimes you get light, sometimes you don't get light. So you get a pulsating current in the photocell. Now you have a photocell as a detector. So sometimes you get light, sometimes you do not get light. As when you get light, you will get current. When you do not get light, you do not get current. However, light from the flame gives steadiest current as it falls steadily on the photocell. Now, what happens is the steady, where there is a steady current, you will get a, say, DC type of signal. Where there is pulsating current, we get a pulsating type of signal. So we subtract the DC from the AC current and record the output. In this way, we can get rid of atomic emission. So this is how a chopper works. So this is the flame. Here, if you may record this one, you will get emission only. But from here, if you chop it out, you will see here, light that passes through is emission and the transmitted light. But Here, light is not allowed to pass, so only emission goes. So here you get only emission, whereas in the next slide you see you get emission and the transmitted light. So if you subtract these two, you will get the transmitted light. So next is the sample compartment, this compartment. The sample compartment is really the flame, since it is the flame that the atoms absorb radiation from. So this is the sample compartment. Here we have the instrument similar to that we use in a flame photometer. We have an atomizer. So sample from here is vaporized into the flame. This is the flame. And this is the aspirator, and this is a capillary that sends the sample to the flame. The flame gases flowing into the burner create a suction that pulls the liquid into a small tube from the sample container. It is just similar to that as we have done in flame photometer. 3 steps are required before measurements are possible. One is vaporization, reduction to the elemental state. We have already covered that one, and exposure to radiation. And the first 2 steps are accomplished in the flame. Next is the atomizer. So we will not repeat this one. We have already seen in the case of flame photometer that there are 2 types. One is total combustion burner, and another is the laminar flow burner, where the samples are pre-mixed and then goes to the flame. So this is a cutout of how it looks like. You'll see that this is the capillary through which the sample enters the mixing chamber, and these are the baffles. And the fine spray of liquid that is forced in through this one hits the baffles. The larger droplets will drop out from the drain, and the smaller droplets will move in through these, and then it will go along with the fuel, along with the oxidant, it will go to the flame. Well, there are non-flame atomization techniques also. So we have now talked of flame. There are non-flame atomization techniques such as the graphite furnace atomic absorption spectrophotometer. It has several advantages over the flame. It is a much more efficient atomizer than a flame, and it can directly accept very small absolute quantity of the sample. That means you can apply, you can put slurries, you can put solid samples also. It provides a reducing environment for easily oxidized heat. Those elements which gets easily oxidized, here you can you need a reducing environment which you can get in an graphite furnace. Samples are placed directly in the graphite furnace, and the furnace is electrically heated in several steps to dry the sample, ash the organic matter, and vaporize the analyte ions. So the steps remains the same. Whatever the samples may be, it has to be brought up into its atomic state. So this is, you see, the graphite tube, and here is where the samples are placed, and this is the hole through which the samples are placed on the graphite tube. So very small volume of sample is put here. You see, very small hole is there, so you have to insert the sample over here. So the temperature increases slowly. First, at low temperature, it will be evaporated. Then the sample is ashed at 200 to 300 degrees centigrade. And then the current is increased so that the temperature reaches to 2000 to 300 degrees centigrade. Here, the sample will become atoms. High sensitivity of small samples. Even if you have very small samples, we can do the analysis in this one. So here, you can just see, this is a removable window, and you remove this window, you insert the sample over here. This is the graphite furnace. So you drop it over here, and this tube is heated to very high temperature. So this sample will be vaporized and atomized. And when it is in the form of atoms, light from the hollow cathode lamp passes through this one, and this absorbs this light. Advantages: small sample size, very little or no sample preparation is needed, and the sensitivity is enhanced. Disadvantages: there are background absorption effects, and light may be lost during the ashing stage. Sample may not be completely atomized. The precision is poor than the flame method. Now, I think you do not understand. I think you do understand what is meant by precision. Another problem with this graphite furnace is that since you were putting solid samples, ash remains. So after some time, there will be heaping up of ash, and hence you will have to remove that graphite furnace. Now, background is a main problem. Background correction has to be done to get good readings, and elimination of the background is done by either using a deuterium lamp, or through the Zeeman effect, or through the Smith-Hughes method. So there are three methods of removing background, but the most commonly used is the deuterium lamp and sometimes the Zeeman effect. So it is a serious problem, and it can be corrected using a deuterium lamp. So what is this? What is this background all about? When utilizing a hollow cathode lamp, the measured energy is that from the unabsorbed transmitted light plus contributed from the flame background. So you have two types of radiation. The D2 lamp is placed in place of hollow cathode lamp. The emission, if a D2 lamp is placed in place of the hollow cathode lamp, the emission wavelength is not the same as those required for the sample excitation. So if a D2 lamp is placed in place of the hollow cathode lamp, the radiation of the D2 lamp will not cause excitation, and it will not be absorbed. Hence, there will be no absorption, and the measured intensity is solely due to flame background. So you can just subtract this from the sum total of transmitted light plus flame background. So this one, if you subtract this one from this one, you get only the transmitted light. So the intensity of signal from the deuterium lamp is subtracted from the hollow cathode lamp. This gives the intensity of the sample alone. So here you have the deuterium lamp and the hollow cathode lamp, and you have a chopper. So chopper means sometimes it will pass, sometimes it won't pass. So sometimes this will pass, and this goes to the detector. So you know what is the flame background. Sometimes this one doesn't pass, so this one goes. So here you have the light plus the flame background. So once you have the light plus the flame background, once you have only the flame background, so you subtract the two, you will get only the light of the sample. Then you have the light separation and detection. Once you get the radiation, it has to be measured. That means you need a detector. Now, atomic absorption spectrometer uses monochromators and detectors for UV and visual light. Now you know that the wavelength of emitted radiation by transition metals fall in the UV range also, and that is why you need monochromators in the UV and visual range in atomic absorption spectrometers. And you know that I have already told you that monochromators isolate the absorption lines from the background light due to interferences. Monochromator, the work of the monochromator is to find out to eliminate other radiations and allow only light of a particular radiation to pass through. You can use interference filters also. You can use monochromators also. So that with that you can suppose you want to have a 320 nanometers light. You have a monochromator which will allow light of 320 nanometers to pass through. You can do that by using a bandpass interference filter also. You can use a grating also. Now, discussions on these monochromators is beyond the scope of this lecture. And the detector is the photomultiplier tube. This is the most common detector used in AA's. So this is background correction. So this is the photomultiplier tube I have shown you before also. Single photon is multiplied a number of times so that you get an array of photons. And finally, the signal is transferred to the computer where you can get the final reading. But with all instruments, you need a standardization and calibration. For example, if you want to measure iron, you will have to make a standard curve like this. So you take iron of 1 ppm, 2 ppm, 3 ppm, 4 ppm, 5 ppm. You take 5 solutions of iron and feed them in the atomic absorption spectrophotometer. So you will get readings corresponding to 1 ppm, 2 ppm, 3 ppm, 4 ppm, and 5 ppm. You plot these readings. Well, this is done by the computer itself, and then you get a straight line curve. And this can be this straight line curve can be depicted using an equation. And for any unknown value, if the absorbance that you get over here can be traced back to this point, and it can be fitted into this equation, and you can get the absorbance over here. So absorbance, we can get the concentration of the unknown solution. So we know the absorbance, we can get the concentration. We can just simply put it in this equation and you can get the concentration. Then there are single and double beam instruments. Single beam instruments means only one beam passing through. In double beam instruments, because if the voltage fluctuates, then your signal to the readout will also fluctuate, and hence you will get differences in reading. That is why you need a double beam instrument wherein the single beam is chopped into two, and you get a ratio effect. That means, for example, you have a reading of 2 and 4. The ratio of 2 and 4 is 1 by 2. You have the voltage increases, you get reading 4 and 8. Ratio of 4 by 8 is 1 by 2 again. So similarly, a double beam instrument uses a ratio effect to cancel out any external influences of changes in voltage. So there are certain advances also. Using a hydride generator, I won't go into this. The hydride generators are used, there are elements such as arsenic, mercury, bismuth, which otherwise cannot be done in an atomic absorption spectrophotometer. They have to be converted into their respective hydrides. A bit about hydride generator and a glimpse about how hydride generators work can be had on the lecture of ICP. Okay, so I will stop right now. That's all. I'm in class. I will just call you back. So this is how the whole thing works, and okay, I won't go into all that. So just for example, what are the temperatures that are encountered? So if you use air acetylene flame, it will be around 2000 to 2400 degrees centigrade that we normally use. So in an atomic absorption spectrophotometer, the oxidant is air and the gas is acetylene. So this is it. Whereas if you can use a nitrous oxide acetylene flame to get even higher temperatures, or an oxygen acetylene flame to get even higher temperatures. Okay, I think that would be enough for now. Well,
yes,
Suman,
sir. Yes, sir. Yes, sir.
2 hours continuously is too much for students also.
Yes, sir. Yes, sir. It's a.
So I have the
Next is, sir, continue the next lecture, sir. With.
okay. Thank you so much, students, for joining, and we will continue it sometimes. You can stop.
Yes.
Okay.
Yes, sir. Thank you, sir. Thank you, sir. Behalf of the sir, our whole team, and thank you for behalf of our HOD, and thank you for Dr. Silke, sir. He's the coordinator of this program. Thank you, sir. Thank you for. I hope all the students are benefited for all these topics.
Thank you so much.
Sir, can I end this program, sir? Hello. Sir.